it's already recording. Okay, good. Yeah, when the other guy is a stick, that's the verse. What can you do? All right, so today we're gonna switch gears and start to talk about functional approximation. It's an exciting day. This is why we are here, after all. This is what makes maybe RL unique amongst the many other possible approaches to sequential decision making under uncertainty, that we like to emphasize the use of functional approximators. So today we're gonna look into what good comes out of using functional approximation in the context of planning. So we're mixing this with planning, so we're going to stick to what we set up doing previously, planning. And a little review first about the trajectory that we came through up to this point. So we started with tabular MDPs. Where we have seen that if you have S states, A actions, and you demand that a planner gives you a policy over everywhere, over all states, then no planner will be able to get the job done with a compute time that's less than S squared or S squared times A. And the problem is that S is big. So we don't like this. And then we said that, okay, tabular MDPs, that's one thing. Let's just stick to tabular MDPs still. But maybe we shouldn't demand that the planner outputs an action for every state, because then on its own, that requirement on its own means that, well, the output is really lengthy if you have lots of states. And if you want to use the planner in a closed loop fashion, which is mostly what you want to do, so there's this little planner here. This is the real world, and the planner has access to a simulator. Then the only thing that you need is that a state comes in, goes into the planner, and then for that state, you want to get an action that you can send then to the word. Okay, so this is your planner. And so this leads to the notion of local planning. And for this local planning business, we saw that you can get away with big O something like effective horizon to some polynomial power, I think 5 or something like that, times the number of actions, and the whole thing raised to the effective horizon. So age is like at least 1 over 1 minus gamma if you're in the discounted setting. And so if we don't care about this little glitch here that in the exponent you have the effective horizon, this local planning business basically solves all our problems, because the runtime is independent of the number of states. So that's really great. The idea was just to build this look-ahead tree. You branch with the actions, then you sample next states, fixed number of them. Every such next state, you branch with the actions, and so forth. Do this for a depth, which is the effective horizon, essentially. And then 2 backups in this tree. You can write this as a recursive calculation. And the complexity of this is going to be this, and oops. And you can show that this just does the job. The only problem is that if you actually calculate this bound, okay, so you might suspect this is a suboptimal bound. Other algorithms are going to do better. Perhaps we have a lower bound, right? Which is 8 to the power of h or something like that. So that's a little bit smaller, but it's essentially the same. So there is no possibility to improve the algorithm. You have this dependence on the effective horizon in the exponent, which looks exponential, which seems quite bad if you start to plug in numbers like, you say gamma is 0.99. So this 1 minus gamma is 1 over 100, 1 over 100, which is 100. And so if the number of actions is 2, very, very small problem, then you get something like 2 to the 100. And that's coming from a lower bound. And if you try to run these algorithms, you see that they're gonna just like choke and choke and choke. People have worked on trying to speed them up. We talked a little bit about that. So you can do quite a bit more in that space. But today, we're gonna look at a different idea, which is as ancient as the whole area of dynamic programming, which is what I already alluded to, the use of function approximation, and in particular, value function approximation. So what's this idea? In a nutshell, somehow, I don't know how it was born. I think it was born out of like people trying really hard to solve really big MDPs with very slow computers in the 50s and the 60s. It was ridiculous, but they tried really hard. And they noticed that for many of the problems that they care about, if you numerically try to calculate the optimal value function or whatnot, it tends to be kind of nice and smooth for the problems that they cared about, right? So somehow their state spaces tended to be continuous, or state spaces are discrete, but like just imagine that you have a continuous state space, and you calculate the optimal value function V star, and it's like a nice, like benign looking function. And then they were like, oh, but like if I have a benign looking function, maybe I can compress it. I don't need to, like very finely discretize this interval here to get a very highly accurate approximation of V star. There's better things to do. You can just use, a Fourier expansion, for example, or a polynomial basis expansion. And you can write this value function with respect to these basis functions. So you will have a bunch of basis functions over the state space. So this is your state space. And so maybe you have, like in the Fourier, you would have, I don't know, like this guy, and then like maybe shifted, maybe a higher frequency, and so on and so forth, right? So a bunch of these basis functions. You're linearly combining them. You're hoping that you don't need too many of these basis functions to accurately represent the optimal value function. So maybe this is not quite equal. So maybe there is some little epsilon approximation error going on. But you hope that if that error is small enough, and you would be able to calculate these coefficients. So that's the big question. Can we calculate these coefficients? If we were able to calculate these coefficients, then one step look ahead would do the trick. Right? So the idea would be you do some computation. After that, you get these coefficients. You get a pretty good, highly accurate approximation to the optimal value function. And then after that, okay, so you have, like, let's call this the V hat. Right? So once you have the V hat, then you would say, oh, what is my policy? Well, my policy, let's state as, should be choosing just this. One step look ahead. And now, if you worry about that, okay, but like, oops, how are we going to calculate this expected value in U sampling here, right? Like we have seen already in the previous class that sampling can beautifully deal with this one-step look-ahead calculations, even more complex scenarios. And if V hat is close to V star, then we already derived the result that says that the resulting policy is going to be near optimal. So anyone remembers, like, what's the suboptimality of the policy, of this greedy policy? If I have V hat in max norm epsilon close to V star, well, what do we know about how big is the value function of pi hat, this greedy policy with respect to this approximate value function? How big is this compared to this epsilon? Like, can it be much bigger? How much bigger can it be?
Quite a lot.
Okay, epsilon over 1 minus gamma. Yeah, actually, there is a factor of 2. Yeah, it can explode by this factor of 1 over 1 minus gamma, but then we just say hash hash, like epsilon is going to be small enough so that even this is a small value, right? So we just need to make sure that our epsilon is small compared to 1 over 1 minus gamma. Actually, the scale of this whole thing is 1 over 1 minus gamma. So in a way, this 1 over 1 minus gamma there shouldn't bother us that much. But okay, so here the scale of this guy is 1 over 1 minus gamma. And on this scale, you commit an epsilon error, then it explodes. Okay, you have to be somewhat careful, but if your gamma is, the usual 0.99, then your 1 over 1 minus gamma is this factor of 100. Well, we just need to be a factor of 100 more accurate than originally planned. That should be easy. The remaining problem is, how do we calculate these coefficients? This is a very cool problem, right? Because now we are saying that, okay, we have this belief that the optimal value function can be well represented by these basis functions. We have this MDP. Maybe we have simulator access to it, right? We already agreed that simulator access is good because then we can calculate expected values of value functions with respect to next state distributions by just using sampling. And we should come up with some way of calculating these coefficients. So to be specific, the number of coefficients is going to be D. So theta, this parameter, lives in this space RD. And we're going to assume that D is way, way smaller than the number of states. I'm like, it could be that you have uncountably infinitely many states, and you can well approximate these functions. So big compressions are really, really possible. It's not that unlikely that you can compress things, right? So this whole thing is just about that. Okay, if you have a belief that like some basis functions are good for compressing value functions, how do you get these coefficients? So you can interact with this simulator. So this is the setting that we're going to talk about this week, and then probably next week, and maybe even after that, and then until the end of the semester. We're going to come back to this this problem because this is really the essence of what reinforcement learning algorithms are trying to do, right? Compressed calculation, like without seeing all the states, somehow like you're extrapolating to all the states. Any questions?
Yeah, so previously we've been like assuming that we can have like a worst case MDP, but here like if we assume we have like a worst case function, then this you can't really represent it well.
Yeah, we are radically changing that.
Oh.
Use yours back. Yeah, it's a very good question. We're radically changing the problem. We are being more modest here. We're saying that if we are lucky and the MDP belongs to this family such that its value function is easy to compress using the basis functions that we have, you don't need too many coefficients. In this lucky case, can we do things? We know in effect that in a worst case, in local planning, you can't do better than this, no matter what. That's already established. And if you demand that your policy is defined everywhere over the state space, then it's even worse, right? Like, so that's why we have these lower bounds, so that we see that, well, okay, we're hitting a roadblock there. We need to throw in something new, change the problem in some way. The question then is whether this new setting is reasonable. Like, do we expect this to matter? Like, let's say we work really hard, get some algorithms, like, does it really matter? Well, it seems to do matter, but of course, your bet is as good as my bet. Because this is not about betting on that, like in this particular problem. Like, this is a very general bet in a way. We're not saying that in robotics necessarily you can find basis functions such that the optimal value function can be represented with a few coefficients, or in queuing, or in a specific resource management problem, or whatever, you name it, right? Like, lots of problems can be formulated as MVPs. For which problems is it true that you can represent the value functions with some basis functions, with a few coefficients? That's a different topic. That's not being investigated here. It's more like if someone suggests that these value functions are going to be good for you, know what you do. Like, can you even exploit this? Or even this, like, even if you are given this hint, the remaining computation is so hard that you're doomed anyways. That's the question. So it's a narrower question, if you wish. And does it, like, a follow-up question has to be, okay, where do we get the features, whatnot, right? And that's what we are not investigating at all. I guess a related reasonable question question is, okay, fine. So here we are betting on this linear expansion, right? That I'm showing here. Is this reasonable? Well, maybe yes, maybe no. Lots of stuff works with linear, and what doesn't work with linear, you make linear. So linear is like the first point of investigations. If things don't take off by assuming some sort of linearity, it's hard to believe that they would magically work in the nonlinear domain. So what are we talking about? Okay, is this going to extend anything that we say? Is it going to extend the neural networks? Well, maybe. Who knows? But a special case of neural networks is just the linear stuff. So why don't we clarify first whether things work in the linear case? Like first, we clarified that for the tabular case, things not going to work that well, like without any further assumptions. It's good to know, right? And so we may find that, okay, this is not enough. Like already with linear, this is just still hard, this problem, for whatever reason. And so, baby steps, first steps first. But it's a good question of like, what can you say? We should be discussing this. We should return to this question time to time. Please bug me with this question if I forget about it. All right. Okay. Any further questions related to this setting? Yeah, maybe in the meanwhile I just threw this picture. MDPs. These are all the MDPs. And then, okay, we shouldn't go outside of all the MDPs. But like, there is this tiny little like segment of MDPs. It's like so small that it would hard to even show. These are the MDPs that are friendly with respect to some sort of features. But some sort of other features may serve some other MDPs, and like, who knows, like maybe you can tile all of this, and then it's a question of like, can you bet on the features such that the MDP that you care about is being hit by one of these sets? So that's how I like to think about this question. All right. Okay. So some notation. Very often I like to write, just V star as a function. It's also a big vector. It has as many elements as the number of states. And as such, you could list all the states, and then if it's a linear combination of the features, then you can have this feature vector. So the feature vector at a state would just collect, these components of the basis functions, or D of them, and make it a column vector. And then you would transpose it so that it's a row vector as shown there. And then you can list all of these. I don't know, there are n states. And then there are these coefficients. And then you can just pull out the theta, and there remains this big matrix. So this has D columns. In every column, there is a basis function. And it has n rows, which is the number of states. I don't use S here because otherwise things would not look nice. And so you can pull out the theta, then you can just write this, and then all together, very often we just write that you know, V star is equal to phi times theta, right? Or we also say that V star lives in the span of phi, which is this set. So maybe I put in a star there so that like this is the special vector, and we have all of these other d-dimensional vectors. This is the span of phi, span of features. These are all these functions that you can express with the features. That's a d-dimensional subspace of the n-dimensional big vector space, and here n is much, much bigger than d. So it's like working with subspaces. So far, the assumption that we were talking about is that V star lies in the span of the features. But people have been at this problem for way too long, choose to leave it with one assumption. So there are various other assumptions. So this is called V star realizability with linear features. If you want, you can generalize all of this by putting here an arbitrary subset of all functions defined over the state space. And then you have V star realizability for neural networks, whatnot. Anyways, another assumption would be that for all policies of the MDP, all memoryless policies of the MDP, V of pi, the value function of the policy, lives in a span. Which assumption is stronger? Which restricts the set of MDPs, this set that we can talk with? Like, so you fix this phi, and so this is the set of MDPs where A1 holds. For the same set of features, is the set bigger or smaller? If I consider A2.
I think, yeah, A2 would be bigger.
The set of MDPs that satisfies A2 is bigger or smaller?
Sorry, I guess what I meant is A2 implies A1.
Oh, A2 implies A1. Yeah, that's true. So A2 implies A1. And the reason for that is what?
Just because there's an optimal policy by the theorem.
Right.
The fundamental theorem.
Well, yes, exactly. So the fundamental theorem says that there exists a pi such that V pi is equal to V star, right? So that means that the set of MDPs for which A2 is true is even smaller. It's like this subset. I didn't go out of the other set. Just stick inside. That's where A2 holds. Okay, so whenever A1 holds, whenever A2 holds, A1 holds, but it could be MDPs where A1 holds and A2 does not. There are indeed examples like that, many. So A2 is a stronger assumption. There are other assumptions. So we learned about Q functions, action wave functions. So we can have an assumption that B star is in the span of, well, I should write, I don't know, phi tilde, because phi tilde, its basis functions of state action pairs, right? So it's a different object. And then you can have another one that says that for all policies, oops, pi, q pi is in the span of phi tilde. And again, B2 is going to imply B1. Apologies for the noise. Difficult times for reading. All right. As you may suspect, it is easier to work with the stronger assumptions. So if you have an algorithm that works under the weaker assumption, then it will also work under the stronger assumption. It may be easier to find algorithms that work under stronger assumptions. So we're going to start with B2. So let's assume that B2 holds. We have simulator access. Does there exist a local planner? Could be a planner too, such that with poly A, B, age, 1 over delta queries and computation. The planner induces a policy pi such that this policy is delta optimal. So what do you think the answer is? That's a clear question, but you can just wildly guess. It's okay. I guess my next question is going to be why, anyways. So you would, okay, you need to design this local planner. How would you start? Like, so we have this B2 assumption, right? Like this very, very nice assumption that it's not only the optimal action value function that lies in the span of these features. By the way, I'm going to drop the tilde, so rename phi tilde to phi because I don't like to write it much. It's too much clutter. So you have this very nice assumption, and you want to design an algorithm that makes use of this assumption. Like, how do we start? Give me some ideas. Alex, you're not answering the question. You're asking other questions. Those are good questions. But I guess the answer in general is no, not even the features are related to each other. So we don't, like, that's not so simple. Okay, so we need to design an algorithm, guys. What algorithms do you know about? Like, Give me the names of some algorithms you've heard about in the context of MDPs for me.
Value iteration.
Yeah, you heard about value iteration. Good. Tell me the name of another algorithm that you heard about. There's only one more. Okay, Wesley. Good. What is iteration? So how does value iteration work? So value iteration works by, I don't know, for Q functions, it would start with Q0 being 0, and then Qk plus 1 being updated by applying the Bellman optimality operator to the previous Q. This is a good fit to this assumption that the action value functions of the policies can be represented in a compressed fashion with a few basis functions. So Wesley is nodding. No. What do people think? Yeah. So what's the problem? Yeah, Mehran, do you want to say something? No?
Well, maybe the issue with value iteration is that those iterates might not lie in the space anymore.
All right. So we made no assumption about, we made no assumption that would allow us to conclude that these iterates can be represented in a compressed form. So yeah, this guy, yes, right? Just use the zero coefficients. That's easy. That always works. But how about the next one? How about the next one? Are there value functions of any of the policies? Well, we have not defined this idea. Okay, give me an assumption that you would want to make if you want this algorithm to succeed. What would be the assumption that you would come up with, like that you impose on, like the interaction between the Bellman operator and the span of the features? If you wanted that, yeah. If you wanted this computation to succeed in a compressed form, right? So that would mean that, well, if this was compressed, we should be able to compress this. Well, this is nothing but the closeness of the span of features, or the invariance of the span of features under the action of the Bellman operator. So if you want this to succeed, if you want to conclude that from Qk is in F, okay, let's call this, let's F be the span from now on, right? So this function space. So if Qk is compressible, and from this we want to conclude that Qk plus 1 can be also compressed, and then we just compute the coefficient in some way, we don't know how. And they should hold because we have no control about like what Qk is going to be. The best would be if this holds for any function from F. So if for all Q in F, it holds that TQ is also in F, so that's called closeness, or invariance. And we also write it as like TF, which just means applied operator to every element of this set. So operators can be applied to sets like that. Is a subset of F. So if you want value iteration, if you want to argue that value iteration is going to succeed, you should make an assumption like this. But today we didn't make that assumption, so that leaves us with this other algorithm, which is policy iteration. So how does it work? So choose pi naught arbitrarily. And then choose pi k plus 1 to be greedy. Okay, we said that with respect to v of pi k, but that's the same thing as saying that p of k plus 1 should be greedy with respect to q of pi k, where q of pi k is just this one step bam on look ahead. It's the notation that was introduced previously, right? So this is RSA, and this is this operator that maps value functions to action value functions. So P of V at SA is just the expected value of V with respect to the next distribution at SA. Right, so these are the one-step Bama look ahead values, and pi k plus 1 S is argmax of Q of pi k SA. Right, so that's the greedification. And so now B2 meant that no matter how you come up with a policy, you'll be lucky. Its value function can be compressed. So this sounds right for policy iteration, right? So policy iteration likes to marry B2. They're good friends. And value iteration was a good friend with this closeness assumption. Still remains to be seen whether this can be done, right? Like so far, this is just an idea that if B2 does hold, then maybe there is some variation of policy iteration that we can make work, right? So we can compress the computation that policy iteration does under assumption B2. Okay. So, but there are some details that are left out by this. So how do we do this? How to actually carry out the calculation? Well, we need to compress what? We need to compress this guy. So there exists some coefficients that this holds, but we want to calculate these coefficients. And what do we have? We have the previous policy. We have this pi of k, which is given in this implicit form. So, okay, if this was represented using some features, then this calculation, like at least for, we can point away the policy. We can tell by just looking at So the feature map, in this case, maps state action pairs to the dimensional vectors. And then we can calculate, what the feature map takes for the different actions, multiply it with this shared parameter, and then choose the maximum value. Good. The policy can be point evaluated. That's good. So that should make us hopeful, right? So that's that's neat. But still, the question is, okay, how do you get out? Like, how do you come up with these parameters? Like, these are the values. You need to calculate them. So give me some ideas. Oh, this problem, we can generalize this a little bit, make this sound fancy. It can be phrased as follows. You have a policy pi. This is going to be, let's say, a deterministic policy. And you have B2. And you have a simulator. And you can point evaluate this policy so that means that for any state of your choice, you can get the action that the policy would choose at that state. You can evaluate pi s. Okay. We need to calculate this parameter vector, this d-dimensional parameter vector, such that this parameter vector combined with the base functions gives you, the action value function of this policy. This problem is called the policy evaluation problem. You try to calculate the action value function of the policy. How to do this? You guys I'm pretty sure you know quite a few algorithms that will try to do this.
So the operator is just a linear operator, so you should be able to just solve the matrix equations, no?
So are you alluding to that Q pi is the fixed point of its policy evaluation operator, which is a linear equation, and then somehow just plug in and then solve the linear equations? Let's try. I think that that is a remarkable idea. So how does this work? So Q of pi is the fixed point of this system of equations, right? It's the unique fixed point. And we a lot of times we write these guys together, and then it's a little bit confusing. That's a p pi as well. But this is an operator that maps state action functions, functions over state action pairs to functions over state action pairs. Okay. So with this, so that's just a big matrix, an SA by SA matrix. So you have Q pi is equal to R plus gamma P of pi Q pi. And we also know that q pi is equal to phi of theta. So this altogether is linear. Everything is linear here. You just need to solve it for theta. How do we do this? Well, one idea is to plug in. Well, I'm just making this up in a way, but it's what people do, right? I mean, if both hold, I can plug in and I will get equation, at least one equation. The problem with plugging in is that it may create spurious solutions, right? Because the two equations are replaced with one equation, maybe you lost something. Well, hopefully not. So how big is this system? So the number of unknowns, so the problem is that here, the number of unknowns was q pi. So which are the unknowns? Q pi, that lives in r to the power of SA. It has SA unknowns. That's ridiculous, right? And then there is theta, which lives in RD, which has D unknowns. So in this black box, the total number of unknowns is SA plus D. After doing the plugin, we eliminated the big variable, q pi, which was SA values. We just replaced it with phi theta, because we know that it's compressible. And so the number of unknowns here is D. That's hopeful. That's progress, right? If you want to solve a linear system that has so many unknowns, like SA plus D, you're kind of doomed if you want to list like all those values. You can't do that in time independent of the number of states, for that matter. But if after you plug in, you only have the unknowns. So this is what compressed computation is about, right? Like now we're talking, we only need to calculate D values. But hang on for a second, how many equations do we have here? So these are, you know, like vectors. Like, what's the dimensionality of vector I? That's the easiest guy. So what space does R live in? It's SA, right? So R lives in R to the SA. Oops. So we have SA equations. What are we going to do? Can we solve a linear system that is written with SA equations, has D unknowns in time D, or polynomial in D? It's like a weird system. It's like long, lots of linear constraints, but very few unknowns. If you order it such that it takes the normal form, that would mean that this guy goes to the other side. You would have this very long matrix. It's very few columns, right? And then you would have theta, and that equals R, which is this very long vector, right? So SA. So this is SA. This is D. This is just one. And this has D values in it. So what to do with linear systems like that? I wish I attended all those numerical analysis classes now. Give me some ideas.
SVD.
Whew. Okay. SVD. Taste Alex. All right. LU decomposition. What? There was LU decomposition, subsample rows. What else? Least squares. Oh, Macron is asking, what if this linear system doesn't have any answers? Oh. What if, what, B2 doesn't even hold? Oh my God. So we want a robust solution, right? So maybe that's a good point. If you build a target that only works under a very narrow set of assumptions, and anytime you're deviating from the assumptions, it blows up. Like it's not doing anything useful, no matter how small the deviations are. And that's not really a good algorithm. So you want to relax a little bit this B2, and maybe it's worthwhile to discuss that a little bit. So rather than saying that, okay, Q pi, I certainly know that it lies in the span of these features, you should just say, oh, it lies close, okay? And so if it lies, like epsilon far in uniform norm or max norm, then we expect that we will find a solution which scales with that epsilon, right? So if that is a good solution, that is a good approximation, then we should find it. That's kind of the relaxed version of the problem, robustified, relaxed version of the problem, and that's important, super important. But okay, so we have lots of ideas here: SVD, LU decomposition, subsample the rows, least squares. Do we know of any of these whether they will be computationally efficient? So don't forget that we want poly D A age one of that or whatever, right? Like polynomial time computation independent of S. So any idea that involves just enumerating all the rows or going through all the rows, that's out of question. So if you try SVD very naively, I guess you would run into this problem, but you can probably patch it up. I'm guessing the same applies to LU decomposition. I think these are all great ideas. Subsampling the rows, I really like that. And I also like least squares, because I understand those a little bit better, I guess. So row subsampling, how would that work? Like, what distribution would you use to subsample the rows? by the way, this guy here is just I minus gamma p of pi applied to phi. It's a nice guy. Yeah. Oh, Macron is asking whether it's better to estimate the parameters instead of solving the linear system. Well, aren't they the same? Just different words being used for calculating parameters. We need to calculate those parameters in a way. And if we calculate these parameters, we're going to solve the linear system. So they're the same, kind of. In my mind, at least. There's no big difference between solving this system. But you want a robust method to solve it, and you want a method that scales well and doesn't require you to go through all the state action pairs. Number of states is too big. So subsampling the rows. So Wesley said we should do that. Do you have any more specific ideas about how should we subsample the rows? Okay, not really. That's quick. Uniformly, yeah. That's a bad idea generally. The uniform distribution can really screw you because I can repeat the same row many times, and then your uniform distribution becomes really non-uniform. So it's not too clever. So somehow we have to do something better. Use the steady state distribution of the current policy. What? We don't know that. All right, so maybe you could simulate it or something like that. Okay, long story short, I know some ways of solving this system approximately. I don't know what's the best way. We don't have matching lower and upper bounds. So I can tell you the solution I know of, which kind of works out. And it's based on least squares. And in a way, it's based on choosing the rows in a very clever fashion. And the story starts with least squares, actually. It's quite amazing that this is such a simple problem. We should have a much better understanding of what is the best algorithm for this setting. But at least I don't have that understanding yet. Maybe someone here is going to help me figure out, or like is going to figure it out. All right, so weighted least squares is going to be the name of the day. So weighted least squares is almost like least squares. And okay, so before I go there, let me just say one thing. So this idea of solving the linear system and plugging in, it's very intriguing, but I will go in a completely different way. I will just use truncation because, so that's before we talk about weighted least squares. And that's because Q of pi, it's true, is the fixed point of this operator T of pi. But if you start to iterate this operator, and you iterate it k times by applying it to 0, then you get something very close to Q of pi. We know that, right? There is a geometric rate of convergence. All these operators are contraction with a contraction factor of gamma. So after, I don't know, h gamma delta steps, the error here is going to be smaller than that. All right? And the good thing about this is that we can simulate this. Because this is what? This is just like running the policy for k steps, calculating the return truncated after k steps, and then averaging, right? This is the total discounted return truncated after k steps. So this k step truncated discounted return. And that's easy to simulate. So if you want to know what Q pi of SA is, just run some simulations with the policy. Do it m times. M independent simulation runs. They give you these trajectories. In every trajectory, there is going to be k steps. And there are all these actions. And states. They just come from simulating the policy. Using your simulator. Okay. So if I call this, like here, the initial condition is that S naught is S, and this holds for t greater than equal to 1, and E, all right, so for every I, A naught should be A. So if I call this R hat SA, then the expected value of R hat SA is just this operator applied k times on 0, and its value taken at SA. Right? So we know that the terms that we are ignoring are going to be small because k is big enough. We can run all these simulations. And so in a way, we can measure Q pi up to some error that we can control. This data here by making k large. We can control that error. But apart from that error, like we can arbitrarily precisely measure the value of Q pi at any state action pair of choice. Okay? And we also know that this parameter vector that gives you Q pi. So Q pi at SA is just phi SA transpose theta. And so we could choose a bunch of state action pairs, right, from some subset of all possible state action pairs, and just run least squares, because we are measuring these with this R hat SA with some noise, with some error, but the error is controlled. And we expect that least squares is going to give us a pretty accurate approximation to the true underlying theta. So just, roll out least squares, the simplest thing that you can imagine. Does this make sense? So I mentioned weighted least squares. So I just want to refine this a little bit. So instead of thinking about least squares, let's think about weighted least squares. So maybe the weighting could be helping us to get our thinking straight. You know, weighted least squares is often used when you have non-uniform variance. You have some reason to believe that some points are more important than some others. And here, the question that we're going to ask is that, well, we basically set up a least squares problem. So this is a least squares problem. So least squares or parameter estimation problem. And then the only remaining question is, at what state action pairs should we be running these simulations? So these are the simulations. And then some details like how many of the trajectories are we going to need, and like what should be the length of these trajectories. And altogether, like, can we get away by just measuring these approximate values at a few state action pairs? And if so, which state action pairs should we be using? That is the big question. Like, which state action pair should we be using? Right? Like, how do we decide about what state action pairs to use? So you recall linear regression, right? So this is basically a glorified linear regression problem. It's, let's say, a kind of different drawing, but you have a linear function that you want to estimate, right? And so this is SA, I guess. Well, it's phi SA. This is phi SA, right? Like the feature space. So as you're traveling in the feature space, like the points combine in a linear fashion to give you the value. The feature was one dimensional. This is the picture that you would have. The feature is two dimensional. You have a surface. Can't draw surfaces. So gotta stick with one dimensional feature space for the drawing. And for the different values of state action pairs, you can get features, let's say here, 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 here. Maybe you can also get this. Which features, which state action pairs would you choose if you wanted to measure this line, like you wanted to estimate the line? So if you choose a state action pair, so this corresponds to one state action pair, S1A1, this is S2A2, and this is S3A3. They're very, very close to each other. And this is S4A4. Then you will be able to measure, you know, whatever this function is. So this function could be, you know, like not just like that. It could be like this. It could be like any function. Like it could be totally flat. It's just linear. Right? Just line. Some line. You're gonna measure it, and you're gonna measure it in noise because we have simulation noise and we have some error as well. So you don't exactly get this value. You get some value in the vicinity of this, right? You kind of like when you measure something, then you should be thinking about that, wow, this value is uncertain. So the actual value could be like further up, further down, right? And you can decide to measure here, and then you can decide to measure there as well. Right? And maybe you can even control the precision with which you're measuring things, because you can measure more, and then the noise and the approximation error would also be reduced, and so forth. So, any advice for me where to measure? Yeah, the y-axis is skew. Yeah, that's right. Select the convex hull. Okay, so Vandin is saying select the convex hull. I guess you mean that, okay, if you take an up, like look from the top to the bottom, and note this becomes two-dimensional. So we have the feature space here. So this is feature 1, this is feature D. Then there are all these feature vectors. They are somewhere. And we should be selecting, well, what does it mean to select the convex hull? So does it mean that we should be selecting all the points such that if you take the convex hull of these feature vectors, then these points are the vertices? Yeah. Just mean the boundary. So just select maybe this. Is that good enough? Or all the points? All the red ones. Okay, right. So all the extreme vertices. How about like this figure? Ooh, look at this. I'm being very mean with you. All the points around the boundary. Oh my gosh. So I can make it very bad, right? Like maybe that's an overkill. We don't need all the points, but somehow the extreme points seem to be important here. But it's a very nice answer to this question, like which points to select such that if you're measuring a function and you know that this function is like a linear function of these things that you're measuring at, then you get the best accuracy. And the answer to that comes from what's called the Kiefer-Wolfowitz theorem. So if you take phi, mapping this, let's say, finite SA to RD, there exists C, which is a subset of SA, such that C has at most D times D plus 1 over 2 points. So this is how many corners you're going to need, like how many blue points you're going to need, such that the following hold. if you take the max over all state action pairs of the feature value in a weighted norm then this is going to be smaller than or equal to square root of d. And so this row maps C to 0, 1, such that the sum of the values, so this is a distribution on C. So the sum of the values is 1. And here G of rho is this Gramian matrix, which we all know and love from least squares. And finally, if you have a positive definite matrix P, then this norm is X transpose PX. And so why am I bringing this up? So the reason I'm bringing this up, we won't have time to really connect everything up today. But the reason I'm bringing this up is because if you solve a least squares problem, you might have seen this in statistics classes. The inaccuracy with which you can predict values at a given state action pair, if you solve the least squares problem using data from this set C and weighted least squares with the weighting row, is going to be exactly like this. So this is kind of like the blow-up factor of the error. So if you are measuring the responses with an error of epsilon, then if you solve the underlying weighted least squares problem and some Cauchy-Schwarz inequality gives you that the error blow-up is this quantity here. And the Kiefer-Wolfowitz theorem tells you that to control this error blow-up, you can control it. The blow-up is at most square root of d. And the number of measurements you have to take at different points, so the coordinate of this set C doesn't have to be too large. Roughly d squared points are sufficient. And if you allow me to increase this to 2 times square root of d, so the Kiefer-Wolfowitz theorem is a little bit more precise. It also says that no other thing, like no other design can do better than this. So if you want to run with weighted least squares, then this square root of d is exactly the value you can get. There is an equality here if you consider all possible set C and all possible distributions row. Okay, but if we don't care about like that high precision and we say that, okay, another factor of 2 is fine in blowing up the error, then we can reduce the coordinate of C to almost linear. So d to the log d something plus some constant, 16 or something. That's a theorem by Todd. By the way, this Kiefer person, he's one of my all-time heroes. Is one of my favorite statistics books by him. So, Introduction to Statistical Inference. He never wrote this book, but he was lecturing about this. I can wholeheartedly recommend this book. All right. We're almost there. There was one question that Valentin was asking, and I just want to answer that question, and then I let you guys go. The question was in the context of like this idea that we should somehow select the extreme points here. So how are we going to find these points without enumerating all state action pairs? So that's the question of how to find a small c, which sort of have these properties that the blow-up factor is not too big and so on and so forth. That's kind of outside of the scope here. So we're going to say that the designer of the feature should take care of that. So whenever you give me this feature map, please also give me this set or a set of similar properties. And if you can't, then we're kind of doomed. We don't really know what to do. I mean, maybe there are some answers, but we don't know. I don't know. Okay, so currently, the only answer I can give to you is that if, together with the feature map, I'm also given this set C or some set of similar properties such that this quantity here is under control. So it's not much bigger than what's written here, like it's a polynomial of D. Then if that set is given to me, then I'm good. If you just like give me the feature map and I can access it for every state action pair like that, then I don't really know what to do. Whether there is going to be a computationally efficient solution to this problem at all. Maybe there is one. Maybe there is no. I don't. Okay. So we are just going to run with this. I will, like Matthew, you keep asking me about the textbook. Yes, I will post it on Slack. Great. Yes. So, okay. Actually, the book of Todd, which is about this optimal design question. So the topic of optimal design is exactly this, that like someone gives you a feature map, promises this linear situation, and they are asking the question for various types of feature maps. How can we efficiently compute this core set C? So under various specific circumstances, you can do this computation, but it's like not general that like, yeah, like in the worst case, you probably can't. Because I'm just going to hide, like it's going to be another needle in a haystack problem, right? That like there are some core features, but like how do you know like which order you should be accessing these state action pairs? Like you have not a faintest clue. Like how would you be able to do this? Maybe the very last ones that you're gonna check are the ones that bring down the error, and everything else was just crap. Like here, we go back to this picture here. Then maybe okay. The bad guys are, I don't know, they're green. I don't know. They all live there, right? Like all the state action pairs that you ever check are here. And then there are, I don't know, like 3 other ones that just give you all the information. And if you only measure the function here, you have absolutely no way of extrapolating over there. Your errors are going to blow up because the distances are big there. How do you know? Right? Maybe all the features that you have ever accessed are all zero. So I guess like you can just say in a nutshell that in the worst case, no one can do anything about this. So people who are coming up with feature maps, they better think about these properties. And this property seems to be pretty crucial for designing stable policy evaluation algorithms. So yeah, I think that's the lesson. All right, I stop here. At least I got as far as stating the version of Kiefer-Wolfowitz that we need. And we are going to continue next week from here. Next week? No, not next week. On Thursday. Okay. I'm gonna stay if you have any questions.
Excuse me, I just have a quick question. Maybe it's late to mention, but shouldn't we make the assumption that these 5 functions be linearly independent?
No.
There's no.
Well, if they're not linearly independent, then you can reduce this, right? So you can always reduce the dimensionality if they are not linearly independent. Then the situation can only be better.
Oh,
right?
I see. Thanks.
Yeah. So the part where I said that this square root d is the best possible, that requires that they are linearly independent, but okay, like we don't quite need that. We only need that things are not getting worse than this. Yeah, so this is called optimal experimental design, and it's a whole field on its own. So today we have hardly departed from the silliest setting that one can consider. And it's still quite silly because this assumption that the action value function of all policies lie in a span of features is like a kind of hard, like ridiculously strong assumption. But then we end up with this policy evaluation problem, and then we see that like we're full of questions and few answers, and quite a nice area to be in because yeah, lots of opportunities here for new research, right? Like, what's the best procedure for estimating the action value function in this setting? Why don't we have the answer to that question? Good times, good times. All right.